Last but certainly not least talk of the day is with Gavin UBERTI, a software engineer at OctoML. He's going to talk to us about exploring ML compiler optimizations with microTVM.
Great to be here. I am from OctoML, a company that works heavily on Apache TVM. Apache TVM is an AI compiler. It takes in an AI model and generates code for it, C code, assembly, whatever you need. And compared to things like TF-Lite Micro, Apache TVM is much more like a traditional compiler. It takes in a variety of input formats, lowers them through progressive intermediate representations, and applies optimization passes. TVM is fully free and fully open source. It's an Apache project, so open source just like, say, GCC. And today, I am going to walk through just one of these optimization passes so I can help convey what an optimizing compiler does in the context of AI. But first, how do we compare compilers? We compare C compilers with benchmark programs. We take some code, we see how fast it runs with one compiler, we compare that to, say, a different one, and that over a suite of different programs can give us a pretty good idea of how well these things optimize common code. And this same strategy works for AI compilers. We take some common benchmark models, run them through a few different compilers, and get results. To make sure that we're fair, we of course want to use the same hardware and the same model. And one of the most common sets of benchmark models is tinyML. tinyML perf from the ML perf group of people. They have a few. I have one here, their visual wake words model, which is a simple MobileNet V1 that takes in an image and asks, is there a person in this frame? And Apache TVM's performance was not always great. I have here the results from November, comparing TF-Lite Micro on the left to a few compilers like those from STMicro, PlumeAI, and Apache TVM on the right. But over the past couple of months, there has been a massive push in the TVM community to get our performance to be state-of-the-art. And I'm very happy to say now that we have added more optimization passes, and for models like MobileNet in this case, we are able to beat the previous state-of-the-art by about 30%. You can go try this yourself by running the compiler. It's free, it's open source, and they'll be released in the tinyML perf results when they come out in May. And in this talk, I want to go through just one of the new optimization passes we added, channel folding, that helps us beat this record. Now, first, a bit of a recap. What is MobileNet V1? MobileNet V1 is a convolutional architecture that factors apart regular convolutions into depthwise and pointwise convolutions. You can see that we have alternating depthwise and one-by-one blocks. We have 27 in total. I've had to omit some for brevity. And I also want to point out here that we take in the 1 by 96 by 96 by 3 color frame. This is a quantized model. We're using ReLU. And just like any convolutional model, it starts out big and wide, and then it gets narrower as we progress until it eventually does an average pool, does a reshape, fully connected layer, and then we get our two outputs, the probability that the model is a person and the probability that it is not. Very straightforward. I'm sure most of y'all have seen this before. But what you may not know is that, of course, when we're trying to build person detectors, we will often take a MobileNet V1, train it on ImageNet, and then fine-tune it on whatever data set we want to have. But when we do this, we often end up with all 0 output channels. That is to say, these convolutions, not the depthwise ones, but the one-by-one ones, take in a bunch of channels and spit out a bunch of channels. And oftentimes when we fine-tune a model, many of these output channels in the kernel will be filled with all zeros. A compiler should really notice that and optimize it away. But to to detect that, we need to have a pass for it. And there are a lot of channels to optimize. But in the later halves of these MobileNet models, when we have small frames, small width and height, but a lot of channels, we will often get things like where in the final layer, 90% of the output channels are all 0. So how can we think about getting rid of these? The most important thing I want to emphasize here is that while the output channels in the kernel are 0, the output channels in these intermediate tensors are not. Because the bias values are not 0, and the requantization parameters are not 0. So we can't just go and strip out these channels, because that would change the output of the model and hurt accuracy. It would destroy it. That, again, the channels in the kernel are 0. The channels in the output intermediate tensors are not. They don't depend upon the input, but they are not 0. And furthermore, in the depthwise convolutions, for whatever reason, all these channels do have data. So how can we actually factor out these 0 channels without hurting accuracy? Well, we can rewrite 3 operations. This is not an easy pass to do or to implement. We need to have an intermediate representation of our model. We need to be able to look at that in chunks of 3 operators. But being a real full-fledged compiler like TVM allows us to go do fancy optimizations like this. And here's how it works. We're going to go consider a block of one conv2d, one depthwise conv2d, and a third regular convolution as well. In this case, we want to go strip the 0 output channels from this first regular conv2d on the left. Here's what we do. We first go take in that 1x6x6 by 128 input, and we say, all right, of these 128 outputs that we would have had for the second intermediate tensor there, we know what many of them will have been, 90% or so. They're not 0, but they do not depend upon the input. We can go compute them in advance. We compute what those outputs would have been. Then, because for the depthwise convolution, we know the kernel, we know the weights, we know the bias, we know the requantization parameters, we can go and compute what those output channels would have been once we pass the channels that we already know through the depthwise conv2d. And importantly, because channels do not interact in the depthwise conv2d, and TVM knows this, that's the definition of a depthwise convolution, any input channel that we know in advance going into the depthwise conv2d, we will also be able to compute in advance what the output channel values would have been. But we're still not done. That now we know what 90% of the outputs of that depthwise conv2d block will be, but they're not 0, and we still can't remove them. So what do we do? Well, for this last conv2d, each one of these input channels has its own weights inside this convolution. And we know what those input channels will be. So we can just go multiply our constant but non-zero input channels that we know by the constant but non-zero input weights for that final conv2d block, and we can compute in advance how much that would add to the accumulator. And then we just have to go and adjust the bias by that amount to compensate. So by folding these empty channels into the bias of a later convolution, we can go and strip many of the channels from a fine-tuned MobileNet. And now, this may seem like a really big optimization. Is there treasure everywhere? Are there channels that can just be stripped from all kinds of models? And no. Usually, you don't end up with these vast quantities of sparse channels. There happen to be many inside of the benchmark models for MLPerf Tiny, and there happen to be many for MobileNets in particular. But oftentimes there is something that can be optimized. And being an optimizing compiler lets you go and detect these things and fold them into operations later, just like a regular compiler would go and fold, adding 2 constants. And advances in TVM, like relax, go and generalize this even further to do more folding and math operations. So let's go back to exactly what's being done. we start out with this block of 3 operators, the 1 by 6 by 6 by 128 that has a filter that starts out as being 128 by 1 by 1 by 128. But in this case, 108 of the output channels are 0. So we can go strip those out. That means that the bias will now have 20 elements instead of 128. The filter will be 128 by 1 by 1 by 20 instead of the previous size. And the intermediate tensor output will be the same, 1 by 6 by 6 by 20, because those channels got removed. Same thing for the output of the depthwise conv2D. It's a padded operator, so the sizes stay the same. Still has the 20 output channels. And then we go and fold the remaining 108 that we removed into the bias of this last conv2D operator. And you'll also notice that the output of that final conv2D stays the same size. We're not changing the number of output channels in that convolution yet. So for any other part of the model, doing this folding does not affect the output values at all. It does not touch accuracy. Just like any other compiler optimization, doesn't affect anything. And then the last key is that we can do this repeatedly. That we can go take this block of 3, move 2 operations forward, and do it again, because the entire MobileNet model is composed mainly of these alternating convolutions and depthwise convolution operators. So TVM finds this and rewrites it. But we can generalize a little bit. A very similar trick works for convolutions and dense operators. This very last convolution in the MLPerf tiny benchmark has 90% of the outputs as all 0 channels. So going into the average pool 2D, we know what 90% of those channels will be in advance. They're not 0, just constants. And that means that we know what 90% of the inputs to the reshape operator are, and what 90% of the inputs to the fully connected operator are. They're constants, as are the weights of the fully connected operator. So we multiply them together and adjust the bias of that fully connected op to go and compensate. And just like that, we can also go fold channels out of this last convolution operator. And the end result of an optimizing compiler is a model that takes up less RAM, runs faster, and draws less power. And in this particular case of MobileNet V1, we're able to beat the state-of-the-art by 34%, 137 milliseconds instead of 208. This is just one pass of many that makes this possible. But hopefully, this walkthrough of what an optimizing compiler does gives you some understanding of why these massive performance increases are to be expected. Thank you.
Awesome. Thank you. Any questions for Gavin? Oh my gosh. You got first.
How does the optimization vary with the sparse percentage?
In this case, it's not normal sparsity, right?
Like
we have some
sparse
channels.
input.
Ooh,
Sorry, the sparse input percentage, essentially. Like in this particular case, you said that 90% of the channels are sparse, right?
So 90% of them are all 0s, yes, of the output channels. So as one would imagine, the more that are all 0s, the more we can go factor out. I think a few slides ago, here we go. For the particular model that is part of the MLPerf tiny benchmark, here is the fraction of each layer that has this property. Of course, if more of them are all 0, we can do better. And in any case, the earlier layers are where we spend most of our time anyway. So that's why we only get this 30% improvement despite removing many channels.
Just one question. Does that trick also works on networks with skip connections?
Skip connections for like ResNet?
Yeah.
For ResNet, I have not noticed this property of the all 0 output channels. This seems to be a quirk of MobileNets. But the same kind of constant folding can be done whenever the opportunity exists.
Yeah, because in many networks, in MobileNet V2, V3, you have the same depth-wise, point-wise, depth-wise, point-wise inside the residual connection, or residual block. So do you think you can also apply within one residual block?
For that particular case, where we have a residual connection, we only know or which channels are constants if both operators to the addition are constants themselves. So if we happen to have some channel that was a constant before and is still a constant after, we'd be able to go fold that out with TVM. That is not usually the case. This pass would not be applicable in those situations. But for MobileNet V1, it kills.
Any other questions?
Just a very quick one. Why 3 ops at a time? Is that trial and error, or is it something specific?
It's a great question. Why can't we do just one operator? And it's because if we were to just rewrite that one convolution to go and remove, let me move forward too. If we were to just rewrite that one, the output would be 1 by 6 by 6 by 20, whereas the depth-wise convolution is expecting 1 by 6 by 6 by 128. If we only rewrite one operator, the shapes wouldn't match. So rewriting 3 is the minimum we can do to keep those shapes matching and not touch the accuracy at all. Does that make some sense?
It does, but does it scale up to 5, for example, or is that very dependent on the network that you're dealing with?
Also, if we have patterns like this, where it's more operators together, we can go rewrite on larger numbers too. We just want to go rewrite the minimum number where we find a bias that we can go fold these channels into. It does scale, but you usually don't have to do that.
Thanks.
Any other questions?
This is very interesting optimization. My question is how specific the gain in terms of performance is of the model. Like if I have another model, what can I expect in terms of gain of performance using TVM against, let's say, ST or any other compiler?
I hate to go say this, but the answer always has to be, it depends. This particular optimization is pretty narrow. Usually we don't have this free possibility of many empty all zero output channels. But there are other things that we can go and rewrite that apply more broadly. We can go ahead and use the device, look at what SIMD instructions are available, and decide, all right, does NHWC or NCHW tensor layout make more sense? We can decide, all right, in what order do we want to do the SIMD instructions? How do we alternate those with the memory loads? So we are generally much better than TF Lite Micro and competitive with Plumeria and ST Micro.
Awesome. Thank you very much, Gavin. Great job. Okay, you made it. Congratulations. So I'll take 1 minute and then I'll turn it over to Evgeny. I really appreciate everyone staying. I just want to say I'm really proud to be part of this community. I really think this tinyML community overall, we do interesting technical work. We do it for interesting reasons. We're making an impact on the world. We do it for good. We do it for health. We do it for lots of good reasons. And it makes it really exciting. I like all the people I get to talk to, all the people I get to work with. So again, I'll just remind you of a couple things we've said a couple of times. You got a survey link, so please give us feedback on the whole program today. We're doing it again next year, and we can't do it without you. Right? We need all of you to come up with your ideas for the talks, come up with how we should do it. This year, we really tried to focus, and all the credit goes to Davis and the rest of the whole organizing committee, but we really tried to focus on a balance of deep technology talks and more end user application, how does it get to market, how does it work kinds of talks. And I think the balance worked really well. It was really exciting to see today and yesterday. I hope you all enjoyed it just as much as I did. So thank you all very much again. I hope you all have safe travel. And I'm going to let Evgeny close this out.
Yeah, again, thank you all for joining. It's been 3 amazing days in terms of technical quality, engagement, interactions, having some fun together, couple of drinks here and there at night, and a lot of interactions and engagements and seeing products and everything. Specifically, I would like to thank Davis and TPC for putting all this amazing program together. It was quite a bit of hard work, but I think we gave him a challenge to have more use cases and applications and bring more partners and products, and I think it worked out quite well. Thank you, Davis. And I would like also to thank all of you, obviously, for being here, and also tinyML organization, Olga, Ira, Christian. I think you guys been quiet, and that's a good sign. If things quiet, it's like a good engine. That means it works well. You don't need to do any predictive maintenance type of things. No tinyML for you. You got it works with. And better, yes, of course, yes. And keep an eye on announcement. There is a lot of stuff going on in tinyML. So we have all the communication channels, emails, LinkedIn, everything there, newsletters. So just when you receive them, open up and read all the information. There is a lot of stuff going on there in the tinyML community. And I think we'll see you in a year here and in other events.